Welcome to lecture number 25 for ECE 476 Advanced Embedded. In this lecture, this is an example of the Where's My Car, in this case, Where's My Cat program. If you hit GP15, it locks in your current GPS position and now displays where you are relative to that home position. If I walk around, and the GPS bead on the bottom, see the two actually record pretty darn accurately. Units with a Raspberry Pi Pico and Python. So starting out, GPS is yet another sensor available with the Raspberry Pi Pico. What the GPS sensor will tell you is your latitude, longitude, elevation, speed in knots, and heading in degrees. So with that, you can locate your car or report the distance you are from a previous reference position. You can display your speed in miles an hour, and you can do other stuff. It's kind of up to your creativity of what you do with the GPS sensor. So starting out, the GPS sensors work using serial communication, the SCI interface. This is an interface we haven't talked about yet. SCI is asynchronous serial communication. What happens is you just have a single wire and you transmit data on it. The line idles high. So here's kind of a problem for you. Suppose you had a string of numbers like so. How do you tell where the start of the message is? How do you tell where the end of the message is? Well, you really don't. So what SCI does is the line idles high, and I have to indicate the start of the message somehow. The way it does it is when the line goes low, that's telling the receiver, hey, data's coming, get ready. I then send 8 data bits, each one's a fixed length at 9600 baud, each bit's a 9600th of a second. Then I go high to idle. That way what the receiver does is it waits for the line to go low. When it does, it knows message is coming, start reading it. Now transmitting and receiving are a little bit different. Transmitting is actually pretty easy. I just transmit whenever I want, but when I do that I have to pad the first bit with a 0 and end up the line being high when you're done. When I receive serial data, I really have to use interrupts because I have no idea when the data is coming in. When the serial line goes low, I know the data is coming in. I want a sample right in the middle of each bit, so I wait 1.5 samples. Sample in the middle, repeat 8 times, then I have all 8 bits. That's my serial read. Now timing is critical. I really have to be sampling pretty close to the middle to get the bits correctly. This is why the serial read is actually using interrupts. You can do that in software, but not really needed. That's built into the Raspberry Pi Pico. On the Raspberry Pi, there are 2 serial ports, serial port 0, serial port 1. Port 0 can use any of the ones in purple, pins 1 and or GP0, 1, GP12, 13, or 16, 17, your pick. Serial port 1 can use pins 6 and 7, or 11, 12, your pick. So with it I could actually have 2 GPS sensors or 2 serial ports, 1 GPS, 1 radio transmitter, your pick. What I'm going to be using is actually normally SCI 0 for a single GPS. Later on in this lecture we'll look at differential GPS when we use 2 ports. Now the procedure to initialize the serial port is from machine I import UART. That's the Universal Asynchronous something something RT, receive transmit. That's the SCI port. This tells that I'm going to be using some canned routines that use interrupts to read the hardware or read the pins, actually using hardware. I'm going to use UART 0 at 9600 baud. That's the default for GPS. I'll then set it up as 9600 baud, initialize it, 8 data bits, no parity bits, 1 stop bit, transmit is on pin 0, receive is on pin 1. That's all you need to do to initialize the serial port. Once it's initialized, I can read it. If I do read 5, that reads in 5 characters. Read reads in all available characters. Read line reads in a single line. Read into a buffer stores the data in buffer. There's also read lines, read all the data, and write. So all these are for reads. Writing is you just write to the serial port. So let's illustrate that. Using the serial port, let's read a GPS module. Now the GPS modules use the GPS satellites to tell you your location, and they're actually really easy to use. You just connect power and ground. They're actually fairly cheap. This is for 4 modules, so these are about $5 each. And actually we're getting really cheap. I just connect power, ground, and the only pin I really need is transmit. This is transmit from the GPS. This goes to receive on the Pi Pico. If I do that, I'm receiving data at 9600 baud. In terms of hardware, all you need to do is take your GPS module, connect it to the receive line on the serial port. So this would be for the first GPS module, second GPS module. You pick which one you use. Actually, I'm going to use both of these when I get to differential GPS. I can then read the messages. For example, I have right here a GPS module connected to receive SCI 0 along with power and ground. And funny, I've got this routine. This is just turn on the serial port, port 0 at 9600 baud, using the default, which is receive is pin 1, transmit is pin 0. Read the line and display it. So if I do that, here's my GPS data coming in. And there's a couple ways to do that. If I just do read in 5 characters at a time. So here's reading the first 5 characters that's coming in on the serial port. If I do read line, oops, let's take out the 5. I'm reading the whole line. It reads until I see a character turn line feed. That's the /r/n you see at the end. Let's pause this for a sec. So that's kind of what GPS data looks like. And you see this, these are the GPS messages. Each one has a different meaning. The start is a $sign. They're comma delimited. And also notice right here there's kind of a problem. The GPRMC is one of the signals that we want to look for. That's got the latitude, longitude, speed. It's not showing up with the character turn. That's going to cause problems later on, which we're going to fix a little bit later in the lecture. But there's your GPS data. This kind of shows how easy the serial port is to read. I've got serial data coming in. Just read it, print it. Voila, you got it. Now, what the different fields mean. The GPGGA tells you your latitude right here. Actually, that's the time, latitude, longitude, and the satellites used. Also, your altitude. GPGSA tells you which satellites you're using. GPGSV is the number of satellites in view. GPRMC, this is the one that we're really going to be using. Tells you your time, latitude, longitude, speed in knots, and direction. So depending upon what you want, you've got the different messages you can use. And again, going back over here, oops, going back to Thani. Come on, puppy dog. There you are. Pulling these out, GPGGA, and this tells me here's the time, that I made this recording. This is my latitude, 46 degrees, 53 minutes. Here's my longitude, 96 degrees, 48.1 minutes. Here's my elevation, 295.4 meters. Basically, I'm in my office in Fargo, North Dakota. And the other one, GPRMC, also give you your speed. I'm currently moving 0.3 knots. I'm actually stationary. Okay, so now that we have the GPS messages, I want to be able to read them. Now, again, there's kind of a problem. You'd think that read line would work, but I've got a problem. The message I want isn't starting a new line. I'm missing a character turn line feed right here. So what I'm going to do instead is I'm going to be writing my own routine to receive each message. It is going to start with the $sign. So there's the start of the message. It's going to terminate with the character turn line feed. And everything in the middle is my message. So here, let's do some bottom-up programming to read the GPS sensors. The very first thing I want to do is read the sensor. That is going to be my subroutine GPS read line. And the channel could be either SCI 0 or SCI 1. I'm doing that because later on I want to have two GPS sensors for differential GPS. What this one does is I'll use a flag. The flag is I'm going to keep on looping until I receive a message. And the message is going to be indicated by starting with the character turn and ending with the starting with the $sign, ending with the character turn, ASCII 13. If I see both of those, then I have a valid message, flag is set to 1, and I exit. In the middle, I'm going to start with an empty message. I'm going to return this as a string file, character string. If I see a $sign, start with the beginning of the message. Keep on appending to it until the message is over. Now the stuff coming in on the serial port are actually, it's a binary file. So I'm going to convert that to a character so I get a string file out. So here's how that works. Going over to Thonny. Here is my GPS readline file. Let's see if that works. So when you want to test your file, you write little short snippet codes. So here's a little test routine. I'm going to keep on looping, read the current line, and print it, just to see, is it working? And by working, what I mean is it starts with a $sign, ends with a character turn. So let's stop this. And sure enough, all the messages start with a $sign, they end with a character turn, which doesn't print. Gives me a new line. And the important one is this GPRMC, that's the message I really want, is actually starting out as the new line, new message. Okay, so everything looks good. I can now read one line of data. Now let's parse it. Again, this is a string file. I want to pull off this string, that's your time. Pull off that part of the code, that's your latitude. Here's your longitude, and here's your speed. There's also my direction. I'm moving at 250 degrees north. I don't really care at this point. All right, so now that that tested and works, let's do the next level up on bottom-up programming. Let's pull off the fields. Now when I do that, I could use the Python command float. Here's a string. What is the floating value of that? That sort of works, except that if there's an error, like if I start right here, I'm going to crash the program. And I don't want it to crash. I want it to keep running. Just give me an error message. So rather than using float, I'm going to write my own routine, string to number. I'll pass it the string. The string would be like this field in the message. Here's the next field. Convert those to a floating point number. And if there's an error, just set a flag, don't crash. So the first part is pulling out the fields. These are actually fixed locations. So the time is always at locations 7 to 16. The latitude in degrees is right here. The latitude in minutes is there. The longitude in degrees are these 3 digits. Longitude in minutes are these 3 digits. And here's your speed and knots. The string to number routine is this guy. It basically says, this isn't the world's best coding, but it works. The ASCII number that you're sending it, is it 0 through 9 or decimal point? If it's not, you got an error, it's an invalid message. If it is, I'll check to see if it's a decimal point. If it is, set a flag, because that then tells me that if I have to note what numbers 1, 2, 3, each of these, if I read a number, it's times 10 plus x. So the next one's a 4, it's 123 times 10 plus 4. If there's a decimal point, then each one is a decreasing power of 10. So they'll convert these to a number. If you write a routine, you need to test it. So let's test it. I'll check, is the message 123.456? What is the floating point value of that? Is there an error? And it tells me that the floating point value is 123.456, not an error. If I pass it 1G3.456, what's the number? It's going to give me 13456. This ignores this guy. And then sets the flag saying, this is an invalid string, you got a problem. Okay, so that level seems to work. Let's go one level up. Let's now read a channel. What this does is it waits, keeps on going until I receive a valid string. A valid string means I find the R, the third spot is an R, that's the GPRMC message. And the length is more than 52. If that's true, then the time is this field, latitude in degrees, latitude in minutes, longitude degrees, longitude minutes, speed. Okay, once you have a routine, let's test it. Let's go over to Thonny. I'll turn off this while loop, turn on this while loop. I'll read in the latitude, longitude, velocity, time, and print it. And here you can see, here's the time. I'm getting double reads. There's a reason for double reads. Let's stop this. I'm actually looking for 2 different messages. I'm looking for the GPRMC or the GPGGA. So every second I get 1 of each. If I don't want to do that, here, this one's not going to work anymore. I'll just pull out the GPRMC messages. So now you can see I'm getting 1 reading every second. I'm not missing any readings. Here's my latitude, here's my longitude, here's my speed. All right, looks like it's working. Now that I have all those routines, let's have some fun. Let's have a main routine, which is what I call where's my car? Or in the video, where's my cat? What this does is I display my current latitude and longitude and my distance from 0 position in meters. I'll use the push buttons. When I hit button 15, it takes my current position and calls that 0 position. When I hit button 14, it turns on off the recording. And we'll kind of show that in a video. This is the program, Where's My Car? What's displaying on the LCD is your GPS position, latitude and longitude. This is where Fargo, North Dakota is located. And distance from home position. Now if I press button 15, that sets my home position. So you find out what you want to find, like where you parked your car, in this case, where I left my cat. Hit button 15, and it zeroes it out. You can now move around, and it tells you how far you've gone relative to your home position. So this is summer 2024 wildflower mix. When you want to find out where's my cat, you can look at it and see my cat is, well, I am 9 meters south, 0.4 meters west of my cat. There's the cat. To locate the cat, just come back to zero position. And voila, our cat. Some of the other features, if you hit button 14, it turns on recording. Hold it down again, turns off recording. That's the where's my car, in this case, where's my cat function. Okay, once you're done, the resulting data file looks like this. I've got my latitude, longitude, distance from home position in meters, distance from home position east-west in meters. With that, you can now start plotting some data. And kind of a sidelight, the distance in meters, to do that I've got to convert latitude and longitude to meters. Well, for longitude, the Earth's circumference at the equator is 40,000 kilometers. That's from space.com. Meaning at the equator, each degree is 111 kilometers. Each minute is 1855 meters. In Fargo, North Dakota, scaling to 46.8258 degrees north, meaning Fargo, 1 minute is 1269.448 meters. So in the code, go for the Thani, this is the conversion from minutes to meters. For my latitude, the Earth's polar circumference is 40,008 kilometers. Each degree is 111 kilometers. Each minute is 1852 meters. So again, back in the code, I can use this guy to convert to meters. So with those conversions, if I know my latitude and longitude, and I know the distance from a reference point in minutes, I know the distance in meters. So that's kind of how the previous program works. How about noise? How accurate is GPS? Well, it kind of depends upon which GPS module you're using. I'm using a $5 GPS module from Amazon. If I just let it sit still and measure distance, it's going to drift. So trying that. Placing the GPS sensor outside, letting it sit for 10 minutes. This is what the reading was. It's drifting from about -6 to +7 meters. What that tells me is I don't really know my position exactly given this GPS sensor. It is within about 5 or 6 meters. You can get better ones, but they're more than $5. I can do some statistics on this. Given the data, I've got a mean, has a standard deviation. The mean is the average displacement from where zero position is. The standard deviations measure the spread. From statistics, if I go 1.66 standard deviations left and right, that captures 90% of the area. So the 90% confidence interval for these two sensors is about ±3 meters, ±4.5 meters. Now, rounding, these are good to about 5 meters. If I start moving, the noise actually goes down. And you kind of see that if I walk around a rectangle, just walking around my house. The red line is the path that I took. The blue line is the reported GPS reading. And you kind of see the GPS drifting. While I'm moving, it's not as bad as ±5 meters. It's more like ±2 meters. So accuracy does get better when you're moving. But still, 2 meters ballpark. It's kind of hard to say exactly without knowing your reference position. So just eyeballing it, I'd say about 2 meters. So that is GPS and the program, Where is my car? Or in the video, Where is my cat? Well, one way to improve GPS accuracy is, can I get rid of the noise? Well, to do that, you need to know where the noise comes from. Some of the noise could be uncorrelated, just noise from the sensor. Some noise could be correlated. Suppose I had two sensors. Some of the noise comes from atmospheric disturbances, the GPS satellites intentionally scrambling your position so you don't know exactly where you are. If that's the case, then two sensors at the same location at the same time should have the same noise. If I take the difference in the two, the correlated part of the noise will cancel, and I'll know where I am with much higher degree of accuracy. That's called differential GPS. So let's try that. Let's see, can I improve the accuracy of my GPS sensor by using two sensors? I'm going to have one sensor on SCI 0, one sensor on SCI 1. I'll read both sensors at the same time, take the difference in positions, and see, does the noise cancel? That's differential GPS. Well, to do that, it's actually pretty easy. I'm going to have a global variable called error flag. On each of these reads, it's going to set the flag if the message was not received correctly. I will then check. Let's check your position on sensor 0, check your position on sensor 1. Keep going until I have a valid reading on both sensors. Once I have a valid reading, take the difference in the two, and that's my improved measurement. So presumably one sensor is stationary, the other one's moving. So this one's moving around, this one's fixed. If I know the fixed position, I know where the moving one is relative to the fixed position. I've got a better reading of my actual position. So that's the idea. Well, let's try it. Using the same code, here it is. Yada, 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 yada. Here it is. Same code. Read two sensors, send them to a file, and then display it. So if I start with the two sensors being stationary, then here's the reading on GPS 0, here's the reading on GPS 1. What I was really hoping for is that these two would be going in unison, meaning highly correlated. If I look at them, they don't look to be that similar. That shows up in statistics. If I take the standard deviation of sensor 0, standard deviation of sensor 1, take the difference in the two, ideally the standard deviation should be 0. Actually, the standard deviation got bigger. Likewise for east-west, the noise actually got worse, which is not really what I was hoping for. Well, let's see what's happening. Let's do some correlation, do some statistics. The correlation coefficient is from Random Processes, lecture number 19. This calculates how much two data varies together. If the correlation is 1, as one goes up, the other one goes up. If the correlation is -1, as one goes up, the other one goes down. If the correlation is 0, then the two are basically uncorrelated. What I'm hoping for is a correlation of 1. Correlation of 1 is good. That means when I subtract the signals, the variance will subtract, and the noise goes away. If the correlation is 0, that's bad. In this case, the two data sets are uncorrelated. When I subtract the data, the variance adds. To calculate the correlation coefficient, find the covariance between the two variables, then calculate the correlation coefficient. In MATLAB, I've got my data, x0 and x1. The numerator is the covariance. That's the mean of x0 times x1 minus the mean of x0 times the mean of x1. The denominator is the standard deviation of x0 times the standard deviation of x1. The correlation coefficient in the x direction is 0.22. Basically uncorrelated. In the y direction, correlation coefficient is 0.28. Again, basically uncorrelated. So what that means is there's a very weak correlation between the two sensors. Some of the noise is coming from a common source. That's the atmospheric disturbances, the scrambling of the GPS satellites. Most of the noise is not correlated, doesn't have a common source, meaning it's part of the sensor itself. What that tells me is that with these sensors, differential GPS doesn't work. But then these are $5 GPS sensors. You probably need a more expensive GPS sensor for differential GPS to work. But that's kind of the idea behind it. So that was an experiment that didn't really work. But you got the idea. Third topic, GPS speedometer. Finally, let's use the GPS sensor to measure your speed in miles an hour. That's the GPRMC message that includes your speed in knots, and I can convert from knots to miles an hour by multiplying by 1.15077. Now, on the display, the current fonts we're using are too small. I can't see them while driving a car. So let's come up with a big display. I'm going to come up with a set of fonts that is 100 by 200. So this distance right here is 200 pixels. This distance is 100 pixels. And I want to do that without really encumbering the microprocessor. So I'm going to use horizontal and vertical rectangles just because the graphics module is pretty good at horizontal, vertical lines, rectangles. It's really slow when you get to diagonal. And I'm going to use a 7-segment display. So defining 7 rectangles like so, I can display different numbers by making some of them black, some of them white. For example, the number 1, I turn on rectangles B and C. For 2, I turn on A, B, G, E, D. There's 3, decimal point, and so on. Then when I do that, I have a font that's big enough that I can see it. So this is beautiful North Dakota. On a nice summer day, going to be checking out the GPS module. So here you see on the dashboard, I've got the speed on the top and the GPS speed on the bottom. See, the two actually record pretty darn accurately. So to do that, I'll first come up with a subroutine called Big Display. Completely original name. This isn't the world's most efficient coding, but it works. We're just trying to get this to run. So what I do is I pass the number, that's 0 through 9, that's a single digit, and its location on the screen, XY. I then define the two colors, black and white. And then for the different rectangles, that's your A, B, C, D, E, F, G. I either turn them on, white, or off, black. So the number 0, they're all on, except for G is black. The number 2, these are on, these two are off, and so on. There's probably a better way to do this, but, I got it to work, called it good, go on to the next lecture. So this will display my numbers. To display my speed, I'm going to take the speed from GPS and display it as 2 digits, like 99.9. First, pull off the 2 digits. I'm going to multiply by 10, so I get an integer, like 1, 2, 3. That'd be 12.3. Pull off the zeros digit, that's x mod 10, the first one. Divide by 10, mod 10 pulls off the 1's digit. Divide by 10, mod 10 pulls off the 10's digit. I'll then display the 10's digits, 1's digits, decimal point, and throw in a box right here. Gives me the number 12.3. Then the main loop, I set the sampling rate to, well, I'm going to keep on reading the GPS sensor until I get a valid reading. If I get a valid reading, I'll then check. Have I hit button 14? If so, record your speed, or toggle. I either turn on the recording and beep, turn off the recording, double beep, then display it. If I'm recording, write to file. And here's kind of an example. Now for the speedometer's accuracy. Well, this one is actually kind of hard because I don't really have a reference to go against other than 0. As I'm moving, what I can do is hop in my car and set the cruise control. And that's kind of what I did. I set the cruise control to 40, ran for a while, set it to 50, ran for a while, and here's what the data looks like. Here's while the cruise control is at 40, here's while the cruise control is at 50. If I take this part of the data, I can find the mean standard deviation. Take this part of the data, find the mean standard deviation, and you can see that it looks like my cruise control is working. There's a little bit of error. I don't really know where the error is coming from. It could be the GPS sensor is dead on and my car is varying in speed. And not too surprising, there could be headwinds, slight hills, stuff like that. It was a section of 45th Street South that's flat. But again, there could be some variation in the car speed. It could be my cruise control is dead on and the sensor has noise. It could be a combination of the two. I really don't know. All I know is that this is what the recording data was. The recording has a standard deviation of 0.19, going plus or minus 1.6 standard deviations. I have a speed that's good to about 0.3 miles an hour. Again, whether that's the actual speed or measured speed or both, I don't know. But the net result is I have a GPS speedometer. So in summary, GPS sensors are actually pretty easy to use and they're fairly inexpensive. The ones I'm using are $5 from Amazon. With that, you can determine where you are to within about 5 meters, your speed to within about 0.3 miles an hour. Presumably, more expensive GPS sensors will work even better. Also, the GPS sensors communicate with the Pi Pico using SCI protocol. With some coding, the GPS messages can be pulled out of the fields and read fairly easily. What you do with that is up to you and your creativity. And that is lecture number 25 for ECE 476.